Hello everyone. Today we'll present our project called AuditTrace, which is a multi-LLM consensus for compliance auditing in infrastructure as a service code such as Terraform or HashiCorp files. So there are three steps to it. First is the checkout detection, which runs checks on your infrastructure configuration files and detects if there are any configuration errors that you have in your code. But this is a very deterministic one, and it does not tell you the meaning behind the errors. Then there is a three model false positive filter that which where we run three LLM models simultaneously or in parallel and analyze the results through them. And then there is a consensus voting among all the LLM models. So let's look at how it works. So the problem is that on the repository that we are using, that is the TerraCode repository, which has Terraform infrastructure files, there are 385 checkout findings on that. And the strength of Chekhov is that it never misses a rule. So all the rules, whether or not you comply with them, they will be caught. And there are over 500 AWS and Terraform checks built into it, and it runs within seconds. Secondly, it does not have any context, so it only gives you the line where the error occurs, and that's it. And you don't know why the error is occurring or how to solve it. Then there is 30% noise on real repos as well, and you can save up to 200 hours per audit if you run using Chekhov. But the weaknesses are that it treats a continuous integration test bucket the same as a production bucket, and it cannot read comments or file paths or sibling resources, and drowns engineers in prioritized alerts, something that the engineer might not want. So our approach is that clone the repo, then run the checkoff on it, and extract the full Terraform block per finding. And then the judge sends the findings with the HCL context to the three LLMs. And each model independently labels the genuine faults in your configuration files, the false positives, and the uncertain rules that you have. And then there is a voting mechanism where if all the three models agree to the errors, then there is a high likeliness that the error is valid and it needs to be solved. If there's two on three in the consensus voting, then it's likely that it is an error. And if there's just one on three, then it might be a false positive. So we suppress that. So here's how the architecture works. We This is the PDF that states all the configuration rules for the audit, and we distill these policies into a JSON file, and we use the distilled JSON rules onto the GitHub repo and run the checkout. Then we run the three LLM judges and the tiered repo. So how did we evaluate? We had 30 hand-labeled findings within our repo, and out of them, 15 were genuine and 15 were false positives. So 13 distinct checkout check IDs were used for that. As you know, there are more than 500 different checkout errors. We used about 13 of them, and for each item, we did a precision recall F1 and per tier precision. And in the planner evaluation, we did 55 test cases from the CIS AWS benchmark, which is another standard for the configuration of AWS infrastructure. And then we input clause text, severity type, and target resources. And we get the metrics of severity, accuracy, type accuracy, and target F1. So the results that we got were about 85 to 100% F1 score among all the three models, and 0.67 to 0.93 was the intermodal agreement on all the rules. And the joint consensus of all the models of catching all the errors and understanding where the infrastructure is wrong was 100%. So there were five individual errors across three models, and because of the consensus voting, we ended up with zero errors because the models voted on each error, and if there was more agreement than disagreement, then we assumed that the error was valid. And these are some statistics that we have for what we ran. I'll also show you how we are running our program. And these are the results. Finally, uh, the target F1, the severity, accuracy, latency, cost per run, type accuracy, whether it is identifying the correct type of infrastructure error or not, whether it's correctly identifying the correct severity of the error, and the cost per run. As you can see over here, the GPT-4o is quite expensive, and so is the Llama, but DeepSeek is the least expensive of them all. But DeepSeek also takes the most amount of time compared to all of them. In the Bridge Crew repository, we had 385 Chekhov findings, out of which 211 were high severity and 174 were medium severity. And the overall compliance score on that repository was about 87%, as we found out by running our code. So right now, we used a very small annotation set. We could expand this to cover far more different types of infrastructure configurations. Also, we did a little bit of hand curating so that we can send stronger signals to our models so that they can easily capture the errors. And then we used a single framework, that is the CIS AWS framework. Because of that, we cannot test for other infrastructure platforms, and it only tests for Terraform or HCL files, that is HashiCorp language files. And we did not fine tune any models. We have compiled the results among all these models that we already got. We connected them to an open router server and then compiled the results by doing API calls to them. Yeah, so this is the summary. So I'll show you a small demo of how we are running our code. So here, if you come into the terminal and you run, you cd into the backend folder after uh, cloning the audit trace repository, you cd into the backend folder, and then you run the uvcon main app reload command to start the backend. And in order to start the front end, you should cd into the front end folder and run npm run dev. That starts this program that we have over here. In this, we have to mention the repository URL that we want to check for compliance. And these are the three models that we are providing currently for checking the compliance. We can also provide more, but for the purpose of our project, we are only working with three of them. And same goes for a compliance spec. We are only using one compliance spec for now so that we can do it properly. And once you mention these few things, we run the scan. Right now, I've already run the scan, but when you run it for the first time, it will take like a few minutes to run because when you make the calls to the LLM, it analyzes all the reports and then figures out uh, where the errors are. So these are the final findings that we get, as we had even shown on the PowerPoint file. And when you run it, here you can see that you can see all the errors, uh, high probability errors, medium probability errors, and low probability errors. So there's different types of errors. You can hide the evaluation or show the evaluation, and then you can even export your results. So since this is running, it's not exporting, but once you export, then you'll be able to download the JSON file of all the outputs that you have. Now, once it runs, you will be able to see a bunch of lines where the infrastructure configuration files are and where the errors are. Also, we have kept a feature where the LLM suggests changes based on what the error is of how you can fix that error so that the audit itself becomes a way to fix the errors also. So as you can see, these are all the results that we had right here for this repository. You can try out your own repositories and see how it goes. Okay, thank you. That's AuditTrace.